take a look at the following schema. Let's call it in-depth. Notice that we have to repeat the department information, building and budget, for each instructor in the department. So the comp sci department has a budget of 100,000. You see that here. But for every instructor in the comp sci department, we repeat that information. Why might this be a problem? Well, imagine if you wanted to change the budget for the department. You would have to change it everywhere that the department shows up. So you'd have to look through your entire schema, your entire database, and see where comp sci shows up and change the budget there. This can get very messy very quickly. You could accidentally forget to change one, or you could change one but not the others. Our database would end up being inconsistent. Clearly, we don't want that. But then there's also another problem. With this current design, we can't represent a department unless there's at least one instructor who works in that department, who has an ID that we can attach to the department. So let's say we have a math department, but we haven't hired any professors for it yet. There would be no way of representing that in this current schema. To summarize, the issues with this design are that we needlessly repeat data and that it can easily lead to data inconsistency. How can we avoid these problems? The answer is decomposition. We can decompose the table into multiple tables. So let's take a look at our in-depth example again. So we can decompose this in-depth schema into two separate schemas, an instructor schema and a department schema. You can technically split the attributes between the two schemas. So you can technically split these attributes between the two schemas however you would like. But what we're going to see is that not all decompositions of schemas are helpful. For example, if I choose to decompose the schema this way, with building and budget going into department, and ID name, salary, and department name going into a new instructor schema, I can technically do that, but there is a flaw with this decomposition. Because I included department name in the department, because I included the department name attributes in the instructor schema, the department schema doesn't quite function as one might expect. So an instructor is still required in order for me to add a new department name. That's not what we want. By doing the decomposition this way, we're still unable to represent certain facts, like a department that exists with no instructor. By doing the decomposition this way, we end up with what is called a lossy decomposition, because it leads to us losing information. We lose all the information about what departments exist with no instructors. This clearly is, again, not what we want. What we want are lossless decompositions, a decomposition where we don't lose any information. So hopefully you now have a better understanding of the concept of lossless versus lossy decompositions. So now let's take a quick look at the math behind lossy and lossless decompositions, just so that no test or assignment questions can trip you up. So let R be a relation schema. An example of a relation schema is in-depth. So this whole thing here would be called a relation schema. This would be what R is referring to. And let R1 and R2 be the schemas that form the decompositions of R. If that doesn't make sense, give me a second. So for example, R1 would be the instructor schema in this case, and R2 would be the department schema. So these two schemas here make up the decomposition of R, which is this bud here. Now, if the union of R1 and R2 results in R, then the decomposition is lossless. So if I put my R1 together and I put my R2 with my R2, if I put my R1 and my R2 together and we get R out, get the original R out, then we know the decomposition is lossless. Thank you for watching. Please put any questions you have in the comments and I'll answer them as quickly as possible. Bye.